Hello everyone and welcome back to MathandBolt. In today's session, we will be working on 10 problems on formation of differential equation by eliminating the arbitrary constants. So let us begin. Problem number 1. Obtain the differential equation of all circles in the first quadrant touching the coordinate axis. Using the equation for the family of circles with radius r and centered at h, k, we have x minus h whole squared plus y minus k whole squared equals to r squared. And let it touch the coordinate axis. Then h will be equals to r and k is also equals to r. So we get x minus r whole squared plus y minus r whole squared is equals to radius squared. Let this be equation number 1. Here, r is a parameter. Because equation 1 has a single parameter, we will differentiate it once to obtain a first order differential equation. That gives us 2 times x minus r plus 2 times y minus r multiplied to the differentiation of y minus r gives us y prime minus 0, r being a parameter or a constant. Here y prime represents derivative of y with respect to x equals to 0. Factoring out the 2, we have x minus r plus y minus r times y prime equals to 0. Rearranging the terms, we have x plus y times y prime minus r times 1 plus y prime equals to 0. Solving for r, this gives us r is equals to x plus y times y prime whole divided by 1 plus y prime. Let this be equation number 2. Substitute the value of r in equation number 1, we get x minus x plus y times y prime divided by 1 plus y prime whole squared plus y minus x plus y times y prime whole divided by 1 plus y prime whole squared equals to x plus y times y prime divided by 1 plus y prime whole squared. As the denominator 1 plus y prime whole square is common on both sides, we factor it out and this gives us x times 1 plus y prime minus x plus y times y prime whole squared plus y times 1 plus y prime minus x plus y times y prime whole squared equals to x plus y times y prime whole squared. On further simplification, we get x times y prime minus y times y prime whole squared plus y minus x whole squared equals to x plus y times y prime squared, or performing some more algebraic steps, we finally obtain x minus y squared times y prime squared plus x minus y squared equals to x plus y times y prime whole squared, which is the required differential equation. Problem number 2. Form the differential equation for the family of parabolas having their axes of symmetry coincident with the x-axis. The equation representing a family of parabolas having their axes of symmetry coincident with the x-axis is given by y squared equals to 4a times x minus h. Let this be equation number 1. As this equation consists of 2 parameters, a and h, we will differentiate it twice to obtain a differential equation of second order. Differentiating 1 with respect to x, we obtain 2y by using the power rule times y prime, which is again we have differentiated y with respect to x by using the chain rule, equals to 4a times 1. That's because the differentiation of x minus h will be 1. Factoring out the 2 from both sides, we get y times y prime is equals to 2a. Again differentiating both sides with respect to x, we obtain, we're going to use the product rule on the left hand side, and that is going to give us y times y double prime plus y prime whole squared is equals to 0, and this is going to be the required differential equation for the family of all parabolas having their axis of symmetry coincident with the x-axis. Problem number 3. Form the differential equation for the family of parabolas having latus rectum 4a and axis parallel to the x-axis. The equation representing a family of parabolas having latus rectum 4a and axis parallel to the x-axis is given by y minus k whole squared is equals to 4a times x minus h. Let this be equation number 1. Here the equation contains two parameters h and k, so we shall differentiate it twice to obtain a second order differential equation. The differentiating equation number 1 with respect to x, we obtain 2 times y minus k times differentiation of y minus k gives us y prime, where y prime is equals to derivative of y with respect to x equals to 4a. Solving for y minus k, we obtain 2a divided by y prime, and let this be equation number 2. Now we're going to differentiate equation number 2 with respect to x to get y prime is equals to negative 2a y double prime divided by y prime whole squared. So here we have used the quotient rule on the right hand side, and rearranging the equation, we finally obtain y prime whole cube plus 2a y double prime is equals to 0, and this is the required differential equation. Problem number 4. Form the differential equation for the family of curves given by y square is equals to x minus a whole cubed. We have the equation y squared equals to x minus a whole cubed. Let this be equation number 1. As there is only one parameter a, we shall obtain a differential equation of first order. Differentiating equation number 1 with respect to x to get 2y times y prime is equals to 3 times x minus a whole squared. Solving for x minus a, we have 2/3 of y times y prime whole raised to the power of half. Now we will substitute 2 in equation number 1 to get y squared is equals to 2/3 of y times y prime whole raised to the power of 3 over 2. Performing a little bit of more algebraic steps, we obtain 8 times y prime cube is equals to 27y, and this is the required differential equation for the family of curves given by y squared is equals to x minus a whole cube. Problem number 5. Form the differential equation given by y equals to e raised to the power of ax. Here we have an exponential function given by y equals to e raised to the power of ax. Let this be equation number 1. As we have only one parameter a, we shall differentiate equation number 1 once to obtain a first order differential equation. Now differentiating 1 with respect to x to get y prime is equals to exponential function e raised to the power of ax multiplied to a, which is obtained by using the chain rule and differentiating ax. So we can replace e raised to the power of ax with y. So that was going to give us y prime is equals to a times y. Solving for a, we have y prime over y, and let this be equation number 2. Substitute 2 in 1 to get y is equals to e raised to the power of y prime times x divided by y. Taking the natural log on both sides, we have natural log of y is equals to y prime times x divided by y, or x times y prime is equals to y natural log of y, and this is the required differential equation. Problem number 6. Form the differential equation for the family of curves given by y squared minus 2ay plus x squared is equals to a squared. Here we have the equation y squared minus 2ay plus x squared is equals to a squared. Let this be equation number 1. As there is only one parameter a, we shall differentiate it once to obtain a first order differential equation. Differentiating 1 with respect to x to get 2 times y prime minus 2a times y prime plus 2x is equals to 0. Factoring out the 2 from both sides, we have y times y prime minus a y prime plus x is equals to 0. Solving for a, we have x plus y times y prime all divided by y prime. Let this be equation number 2. Substitute 2 in 1 to get y squared minus 2y. In place of a, we are replacing it with equation number 2, that is x plus y times y prime divided by y plus x squared equals to x plus y prime over y prime whole squared. Performing some algebra which is left as an exercise, we obtain y prime squared times x squared minus 2y squared minus 4xy times y prime minus x squared is equals to 0, which is the required differential equation for the family of curves given by y squared minus 2ay plus x squared is equals to a squared. Problem number 7. Form the differential equation for the family of curves given by y equals to a times e raised to the power of twice x plus b times e raised to the power of negative 2x. So here we have y is equals to a e raised to the power of 2x plus b times e raised to the power of negative 2x. Let this be equation number 1. Now because one has two parameters a and b, we shall differentiate it twice to obtain a second order differential equation. Differentiating one with respect to x, we get y prime is equals to a times e raised to the power of 2x, and this will be multiplied by a factor 2, which was obtained by differentiating 2x with respect to x. Here we have used the chain rule. Similarly, we have negative 2b e raised to the power of negative 2x. Here negative 2 was similarly obtained by differentiating negative 2x with respect to x. Let this be equation number 2. Differentiating 2 with respect to x, we get y double prime is equals to 4a times e raised to the power of 2x plus 4b times e raised to the power of negative 2x, and this will be equals to 4y, where we have replaced the factor a times e raised to the power of 2x plus b times e raised to the power of negative 2x with y taken from equation number 1. We can rearrange this to finally obtain y double prime minus 4y is equals to 0, and this is going to be the required differential equation. Problem number 8. Form the differential equation for the family of curves given by y is equals to a times cosine of nt plus b times sine of nt. So here we have the equation y equals to a times cosine of nt plus b times sine of nt. Now because equation number 1 has two parameters a and b, we will differentiate it twice to eliminate them, and in doing so obtain a second order differential equation. So differentiate 1 with respect to x, we obtain y prime is equals to a times differentiation of cosine of nt will be negative sine nt times n plus differentiation of b sine nt will give us b times cosine of nt times n, and let this be equation number 2. Now we will differentiate number 2 with respect to x, and that is going to give us y double prime is equals to a times negative cosine of nt times n squared plus b times negative sine nt times n squared. So in this next step we are going to take negative n squared as the common factor, which will get multiplied to a times cosine of nt plus b times sine of nt, and that can be replaced with a, equation number 1, and this finally gives us y double prime plus n squared y equals to 0, which is the required differential equation. Problem number 9. Form the differential equation for y equals to 2 times x squared minus 1 plus c times e raised to the power of negative x squared. We have the equation y equals to 2 times x squared minus 1 plus c times e raised to the power of negative x squared, and let this be equation number 1. Here we have a single parameter c. We eliminate it by differentiating it once to obtain a first order differential equation. So differentiate 1 with respect to x to get y prime equals to 2 times the differentiation of x squared minus 1 will be 2x plus c times differentiation of the exponential function is the function itself. So we have e raised to the power of negative x squared times we need to differentiate negative x squared by using the chain rule, so that will be equals to negative 2x. Simplifying the terms, we have 4x minus 2x times c times e raised to the power of negative x squared. So let this be equation number 2. Now from equation number 1, we can isolate c e raised to the power of negative x squared to get y minus 2 times x squared minus 1 or y minus 2x squared plus 2. Let this be equation number 3. Now we will substitute 3 in equation number 2 for the value of c e raised to the power of negative x squared, and that is going to give us y prime is equals to 4x minus 2x times y minus 2x squared plus 2, which will be equals to 4x minus 2xy plus 4x cubed minus 4x. 4x and 4x will get cancelled out, and this finally leaves us with the differential equation y prime is equals to 4x cubed minus 2xy. Problem number 10. A raindrop evaporates at a proportionate rate to its surface area. Create a differential equation relating the rate of change of the raindrop's radius. So we suppose that the volume of the raindrop is equals to 4 over 3 pi r cubed, let this be equation number 1, and surface area is given by 4 pi r square, let this be equation number 2. As the raindrop evaporates at a proportional rate to its surface area, we have rate of change of volume V is directly proportional to the surface area S. So rate of change of volume with respect to time t will be equals to negative alpha times S, where alpha is a constant of proportionality. The negative sign indicates that the raindrop is shrinking in size due to evaporation. Now using volume V is equals to 4 over 3 pi r cube, we have differentiation of 4 over 3 pi r cube with respect to t is equals to negative alpha S. 4 over 3 pi is a constant, so we have pulled it out, so that will be multiplied to the rate of change of r cube, which is equals to negative alpha times, so the surface area is given by 4 pi r squared, which gives us 4 over 3 pi times 3r squared, so that is the derivative of r cube with respect to t, multiplied to derivative of r with respect to t, which was obtained by using the chain rule, and this will be equals to negative 4 pi r squared times alpha. So we factor out the common terms from both sides, and that finally leaves us with rate of change of the radius r of the raindrop is equals to negative alpha, which is decreasing at a steady rate of alpha.